today's class, we're going to be looking at the ideas at the end of Chapter 6. Chapter 6 is all about the electronic structure of atoms, thinking about where electrons can be found and their energy. At the start of the chapter, we explored some properties of light, considered quantized energy, and an initial model of the hydrogen atom proposed by Bohr. We moved to the more modern description, Schrodinger's model, when we looked at quantum mechanics. And now, in the end of the chapter, we're going to see what does it mean to move beyond the hydrogen atom for scenarios in which we have more than one electron. Those are many electron atoms. We want to be able to determine the electron configuration and connect that to the periodic table. This idea of many electron atoms, so far when we were looking at quantum mechanics, we are only describing one electron being present. But clearly we have to go beyond that. That is what we're going to consider in today's class when we consider many electron atoms. As described here in the book, to do that we must consider the nature of the orbitals and their relative energies, as well as how the electrons populate the available orbitals. This is going to be an important skill for us this semester. So first of all, what are many electron atoms? If we look at the pre-class activity, it asks us to identify which of the following are many electron atoms. If it has more than one electron, it is a many electron atom. Chlorine, atomic number 17, is a neutral atom, has 17 electrons. Helium has 2 electrons, but if we're considering the helium plus cation, that only has 1 electron. Hydrogen has 1 electron. Hydrogen minus, that's the hydride anion, that would have 2 electrons. So we have an example of a many electron atom which is neutral, which is chlorine, and one that is an anion, which is the hydride. So we got to be able to determine whether we have only 1 electron present or more than 1 electron. In this particular figure, we see the atomic orbitals for a many electron atom. We've seen a similar image when we were looking at the hydrogen atom. So an initial task, let's compare and contrast those. How does this diagram compare with the one that we saw for the hydrogen atom? On the left, I show the hydrogen atom, a single electron, and on the right, the many electron. So if we're going to compare these, I see a few similarities. The number and the type of the atomic orbitals have remained the same. I see a 1s atomic orbital on each, a 2s, a set of 2p's. So we haven't added or removed the atomic orbitals, but we've made some adjustments. The orbital subshells have remained the same. I see a group of 3 2p atomic orbitals, a group of 3p, a group for the 3d. So the groupings for the subshells have remained the same. I also see the 1s atomic orbital is still the lowest in energy. So those would all be similarities. How about some differences? Well, the ordering of the subshells have changed. For a 1 electron system, the energy is entirely due to the principal quantum number n. The 1s is lowest in energy, the 2s and the 2p are the same, and the 3s, the 3p, and the 3d are all the same. So for a 1 electron system, the principal quantum number tells me the energy. If I look over for the many electron, that has changed. The 1s is still the lowest, then it goes 2s, and then the grouping for the 2p, 3s, 3p, 4s, 3d. So the ordering of the particular subshells has now changed. The energy of the atomic orbitals now depends on both n and l. This particular ordering, 1s, 2s, 2p, 3s, 3p, 4s, 3d, we're going to use that particular ordering quite often in today's class. Now we might ask, why are there differences? For a 1 electron system, like hydrogen, we have 1 proton and 1 electron. And it's the interactions between that positive charge and the negative charge that leads to the different energy levels. As soon as we get to helium, we have 2 protons, and now we have 2 electrons. Turns out when we have 2 electrons, that makes a big difference because now we have interactions between those electrons themselves, repulsions that are acting between them. This additional repulsion, this is going to lead to changes in the relative ordering of the energy levels. That's going to be something that we look at quite a bit in Chapter 7, but we're going to use that idea in today's class when we determine the electron configuration. This figure shows a 1s atomic orbital there at the bottom. Remember, each box is an atomic orbital. So a few questions. How many electrons could be in a 1s atomic orbital? What might its quantum numbers be for the electrons? And then how would the answers there be related to the Pauli exclusion principle? Take a moment, share your ideas on this. When we are populating that atomic orbital, we can have a total of 2 electrons. We're going to look at these representations here in just a moment. 2 electrons can be found in the atomic orbital. One would have an arrow pointing up and one an arrow pointing down. This is referring to a spin up and a spin down electron. This notation 1s2, 1 is the principal quantum number, s is the orbital, and the superscript 2 is telling me how many electrons are in that. The possible quantum numbers for a 1s atomic orbital: n is 1, L is 0 for an s orbital, m sub L equals 0, and the spin could either be positive 1/2 or minus 1/2. These are the quantum numbers that correspond to the 2 electrons that could be in a 1s atomic orbital. How are these related to the Pauli exclusion principle? The Pauli exclusion principle says no 2 electrons in an atom can have the same set of 4 quantum numbers. This leads us to that an orbital can hold a maximum of 2 electrons and they must have opposite spins. If these electrons are going into a 1s atomic orbital, they have the same n, L, and m sub L values, so therefore their spins must be different. So this is saying each of the boxes that we have then, each of the atomic orbitals can hold a maximum of 2 electrons, with one being spin up and one being spin down. In section 6.8, we begin to apply this idea. A really important skill that we're going to use again and again is writing the ground state electron configuration. Ground state is a term that means the arrangement of the electrons in the atomic orbitals that is lowest in energy. And we'll often be using the periodic table to determine this. So some initial questions. What is the maximum number of electrons that could be in a 1s orbital? How about in 3p orbitals or 5d orbitals? A given atomic orbital we just saw can hold 2 electrons. So in an s orbital, I could put 2 electrons. If I have 3p orbitals, each of them could hold 2, so that adds up to 6, or 5d orbitals, that would add up to 10. Now, why do you think we're looking at these particular groupings? 1s orbital, 3p orbitals, and 5d orbitals. Share your thoughts. If we look at our particular groupings, we see that the subshells of the atomic orbitals are degenerate, which means they have the same energy. An s orbital, whether it's a 1s, 2s, 3s, is all by itself, but then we have a grouping of 3p orbitals that go together, or 5d orbitals that go together to form a subshell. These are called degenerate atomic orbitals. Degenerate means they have the same energy. They're on the same energy line. We're going to see groupings like this when we connect atomic orbitals to the periodic table. This table shows the orbital diagram for a lithium atom in the ground state. In the electron configuration, 1s2, 2s1. And we're asked to complete the missing parts of the table. The orbital diagram that is showing the box representation for the atomic orbitals, 1s2, 2s1, that's the electron configuration. It's showing that there are 2 electrons in the s orbital and 1 electron in the 2s. The table that is referenced here, table 6.3, also shows orbital diagrams and electron configurations, and the e-text has a discussion for how we construct that. The periodic table is also useful. So take a moment, try to complete the rest of the table. Try to complete the rest of the table including identifying the neutral atom, the orbital diagrams, or the electron configurations. So as we look at this, 1s2, 2s2, 2p2, so I'm seeing what's in the orbital diagram, and I'm saying out loud what the electron configuration would be. That adds up to a total of 1, 2, 3, 4, 5, 6 electrons. 6 electrons is carbon in the neutral atom. So this would be the orbital diagram for carbon and its electron configuration. If I move on to oxygen, I now have a total of 8 electrons. 1s2, 2s2, 2p4 gets me a total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. If I'm thinking about its orbital diagram, I would put 2 electrons into the 1s, 2 electrons into the 2s, and when I'm beginning to think about populating the 2p, I have to add a total of 4 electrons. This is how I do it. I would add 1, a second one into a different atomic orbital that has the same spin direction, a third, and then I would go back and begin to pair them up. This idea of putting in the electrons into a degenerate set of orbitals, the 2p all have the same energy. I'm putting them in independently with the same spin before I begin to pair them up. A lithium cation, a lithium neutral atom has 3 electrons. If it's a lithium plus cation, it's down to 2, so that would be 1s2, and this would be the orbital diagram. And then finally for the chloride, within the chloride I have a total of 17 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. It's the anion, so I've added 1 more to get to 18 electrons. And then finally for sodium, 1s2, 2s2, 2p6, 3s1. I'm using the same ordering in each of these cases, the same ordering for the atomic orbitals. A lot of information within this particular image. What questions do you have? Here we see more questions involving orbital diagrams. This figure shows the orbital diagrams for the electron configuration 1s2, 2s2, 2p3. So they all have a total of 1, 2, 3, 4, 5, 6, 7 electrons. But notice they've populated the orbital diagrams in different ways. The Pauli exclusion principle and Hund's rule are used to identify which of these represents the ground state. So we have various questions. Which of the orbital diagrams is the ground state? Which ones are at odds with the Pauli exclusion principle? Which ones are at odds with Hund's rule? And how might we correct them? We've already discussed the Pauli exclusion principle. How about Hund's rule? Hund's rule says that when filling degenerate orbitals, meaning ones with the same energy, the lowest energy corresponds to having the number of electrons with the same spin being maximized. Let's see what that means. So before we get seeing the answers, give this a try. Which of these questions can you answer? Let's now go through them. Which orbital diagram is the ground state? C is the ground state. In order to determine why C is the ground state and not the other ones, let's see what's incorrect with the other ones. Choice A is inconsistent with the Pauli exclusion principle. Remember with the Pauli exclusion principle, every quantum number, every electron must have a different overall set of quantum numbers. And if I look closely, this box has 2 electrons that would have the same N, L, M sub L, and M sub S values, and we can never have that. So A violates the Pauli exclusion principle. B and D are not consistent with Hund's rule. If we look within B, remember our plan is we want to add the electrons independently to the boxes pointing in the same direction before pairing them up. And we did not follow that rule here. Similarly, in case D, I like that they're all in different atomic orbitals, but the spins are not all consistent. Spin up, spin down. This right here is not maximizing the spin. That's what Hund's rule is telling us. So the best choice would have been C. How might we make some corrections? So within choice A here, if I want to make that consistent with the ground state, I would have had to take one of these electrons and shift it over. And by shifting it over, well, that's changing the m sub L value, because each of the boxes represents an atomic orbital with a different m sub L value amongst these 2p. How about in this case? I would need to shift one of the electrons, and if I were to shift it, instead of being spin down to spin up, I would have to both change the m sub L value and the m sub S value. How about here for D? What would we need to do to correct that? What would we need to do to change the quantum numbers to make it consistent with the ground state? In this case, I think we need to change the spin of this electron. We would need to change the m sub S value. Changing the m sub S value makes it so the spin is now pointed in the opposite direction. When we're writing electron configurations, we'll frequently use the condensed electron configuration. This would be shorthand for us. The condensed electron configuration for sodium is shown here. We have these brackets with this element neon in there. What does the symbol brackets with neon represent? That's the electron configuration for neon itself. The electron configuration for neon, 1s2, 2s2, 2p6. So in this shorthand for sodium, we could say start with this noble gas and then tell me what comes after it. So we could start with the electron configuration for the noble gas and then identify what comes after it. That's what the condensed electron configuration is telling us. We can now connect this to the periodic table. So here's a somewhat strange looking periodic table. This one's showing the different regions of the periodic table and the atomic orbitals that we're filling there. So we see way over on the left hand side, we are filling s orbitals. We've got a group here for the p orbitals, a group here for the d, and a group here for the f. When we are constructing the overall electron configuration, we begin with the 1s, so that would be from hydrogen and then helium. Then after that, we work from the 2s to the 2p, the 3s to the 3p, the 4s to the 3d to the 4p. So we're just going from one block to the next. 5s, 4d, and 5p. 6s, 4f, 5d, and 6p. And then finally 7s, 5f, 6d, and 7p. So these are the different groupings that we have that are different regions of the periodic table that we now see correspond to the different sets of atomic orbitals that we're adding electrons to. This top elongated periodic table oftentimes is shown in a format you're more familiar with, which is here at the bottom. So what they've done at the bottom one, instead of having the whole group of f atomic orbitals in between the s and the d, it's just sort of slid out and it's shown at the bottom. But we still have the same idea where the s orbitals are in the first two columns, the p orbitals are the set on the right hand side, and the d ones are in the center. And this really helps if we're trying to determine the electron configuration. So let's say we're trying to figure out the electron configuration for selenium, Se. If we're writing the condensed electron configuration, the previous noble gas would have been argon. So we could say, let's begin with argon and then identify what comes after that. Working across the next set of rows, we'd have to add to the s orbitals. This is the 4s, because we had n equals 1, 2, 3, 4s. When we then begin to populate our first set within the transition metals, those begin with the 3d, and then we move over to the 4p. So knowing the different regions and the principal quantum numbers that go with them, that really helps us. So we can see for selenium, we'd start with argon. 4s2, 3d10, 4p1, 2, 3, 4. Let's give that some practice. It says add the missing elements or electron configurations to the table. And if there's an entry where we see both the element and the electron configuration listed, evaluate that. Is that electron configuration consistent with what you would have predicted? Work through this and use the periodic table. Let's look at the first two columns. So we see that we need a value for calcium, electron configuration for calcium. That would start with argon, and then 4s2. Titanium would be beginning with argon, 4s2, 3d2. If we go down here for manganese, that would begin to have the argon, and then what comes after that? 4s2, 3d1, 2, 1, 2, 3, 4, 5. We see we could also reach nickel. What if it's argon 4s2, 3d10? That would be corresponding to zinc. And then if we're trying to get gallium, argon 4s2, 3d10, 4p1. Let's evaluate. Now let's go on and consider whether the values that are listed were ones that would be expected or not, based on the pattern that we are using with the periodic table. If I'm considering here for chlorine, neon 3s2, 3p5, I see chlorine that could begin with a neon, and then what's beyond that? 3s2, 3p1, 2, 3, 4, 5. Okay, that's what I would have expected based on the pattern that we're finding on the periodic table. Similarly, if I analyze vanadium, vanadium is right here. That would be argon, 4s2, 3d1, 2, 3. Okay, that's what's listed here for vanadium. But then I begin to have some that are not consistent with the pattern. Chromium, copper, and silver all are different than I would have predicted based on what we've been doing so far. Let's see what's going on there. If I'm looking here for chromium, I would have predicted it would be argon, 4s2, 3d1, 2, 3, 4. I would have expected it to look like this. But notice the actual value. This is what's actually found, not what is simply predicted. One of the electrons, instead of being in the 4s, is now shifted over and is into the 3d. Similarly for copper. In copper, I would have predicted that it would have argon, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. But again, I see that shift. Instead of being in the 4s, I've shifted an electron over to the 3d. The same kind of thing takes place with silver. Within silver, there's once again a shifting over an electron from the s to the d. These are all considered anomalous electron configurations. They're slightly different than what we would have anticipated based on the patterns that we've been following. So what's going on here? We've seen how we have degenerate energy levels, all of the p subshell put together, the p subshell put together, or the 3d. Once we reach different parts of the periodic table, the combination of protons and electrons that are present leads to a shifting, a continued shifting of these atomic orbitals. And in this region right here, we see that the 4s and the 3d themselves are becoming degenerate. It's as if the 4s and the 3d are all on the same line, all on the same energy line. And because of that, we find that there's examples where the lowest energy term is to shift an electron from the s over to the d. The anomalous ones I'd like you to be aware of are these right here: chromium, copper, and silver. So what we've been working on is looking at electron configurations and populating atomic orbitals when we had more than one electron present. Using the periodic table, is going to be an important skill, and this is something that we're going to do quite a bit in the subsequent chapters.